for 77 gigahertz. This kind of length of transmission line, very expensive. So some people call us, our IFRS people, are playing with expensive toy, expensive. Okay, and entry level in terms of investment actually is very high. Okay. Also, we just now we mentioned fiber to the home, right? Optical fiber also is one kind of transmission line. Here we have optical fiber, right? Optical fiber to the home. Okay. Okay. Now let's look at those very typical transmission lines. Very popular one, this coaxial cable, okay? Very convenient for measurement, How, also the disadvantage is not suitable for MMIC, for integrated circuit, right? So in our EE4101E, we have learned, maybe you have forgot, okay? How to calculate. So I have already mentioned, I didn't teach you that part for EE4101E. Anyway, I have mentioned how to calculate the inductance, right? Inductance of this coaxial cable. Also, how to calculate the capacitance between the metallic shell and the center core. Then with the inductance and the capacitance, we can calculate the characteristic impedance, right? Okay? So for your E201E, the electric field, right, static electric field, in that chapter, you can calculate what you can calculate capacitance, right? For the magnetic field, the chapter, what you can calculate the inductance, right? Yes, those can be applied for real application, right? Then also from there, you can calculate. Previously, in older days, we do not have the data. I will show you all these calculations. You can immediately get the results. Okay, I will introduce a very simple tool to all you. Okay, in older days, people have to calculate from what you have learned. Okay, what you have learned in your EE201. First, calculate the from the electric field, right? Okay, calculate from the electric field chapter. Calculate the capacitance, then calculate the inductance, then the inductance divided by capacitance, the square root is the characteristic impedance. Okay? Right? Characteristic impedance is very important parameter for coaxial cable. Okay? So later we will mention in many places is the impedance matching. Impedance matching. With good impedance matching, the power reflection can be minimized, right? Can be minimized. Means the transmit signal can be transmitted to outside. Otherwise, will be reflected to transmitted, then convert to heat. Right? So for big antenna array, we have to use the many approach to take away the heat. Okay, take away the heat. is very painful, especially for instance, for miniature application, the phase array antenna. Phase array antenna could, the phase array antenna could, for bigger phase array antenna could have thousands elements. Then a lot of each antenna element link with transmitter. Okay, huge heat will be taken away. Okay, it will be taken away. So this link can be linked with your EE4101E. Okay, this another here this mentioned in high bandwidth, very wide bandwidth. Okay. This is another very popular transmission line, waveguide. Nowadays, previously, this was manufactured by the typical mechanical approach. Nowadays, this can be printed by using 3D printing. Okay, 3D printing, very powerful. Okay, now we are promoting this. Okay. This also, yeah, this not new for research, right? We need to look at some niche area, how 3D printing can make fantastic job. Okay. Now the industry always ask us a big question is, for big volume, how 3D printing can play the role? This is a big challenge, right? Big challenge for us. Okay. Unless maybe for high-end application, right? Anyway, I just post this. Maybe in the future we could talk with different people. I just give you our view on different new topics, right? Okay. Waveguide, the big advantage is can handle high power. Just now I mentioned for very high power long distance radar, 1,000 kilowatt, have to use the waveguide. Normal PCB cannot tolerate that high power. Okay. Another application for waveguide is for high frequency, terahertz, more than 100 gigahertz. Just now I mentioned this coaxial cable will become very expensive. At the low frequency, this a few dollars, right? A few dollars. At the very high frequency, this in our lab we have ordered 2 cables for 75 to 110 gigahertz. Each cost us $5,000 US. The reason is the mechanic requirement is very high. Okay, this for high frequency, this will become very small. Okay, so that lead the price going up very fast, very quickly. Okay, so for high frequency, when it's for high power, not for high frequency. Okay, then mechanic can make it. Even 3D printing also can do the job. Okay. Also, I bring some. This is waveguide. Okay, waveguide. Okay. Right. This is for maybe for X-band 10 gigahertz. 10 gigahertz. Around 10 gigahertz. Okay. But for high frequency, I'm not sure. I do have this for 60 gigahertz. Then the actual will become smaller. Okay, actual will become smaller. Then inside actually gold plated. Okay, gold plated. Okay. Now, let's introduce the most popular transmission line. This is the planar transmission line. Planar transmission line, why they are popular? Why they are popular? Because they are easier to fabricate using the mass production approach, right? Okay. So this is typical PCB, maybe, or microwave, high-end material. Okay. So this is sandwich structure. At the bottom is a ground plane. On the top, this trace is for transmitting signal. In between is the so-called substrate. Okay, this substrate is characterized by epsilon. Another very important parameter is so-called the loss tangent. Okay, loss tangent. Okay, so in our again, I need to refer to what we have learned in the EE4101E. Okay, we have in the second half we have learned lossy and lossless, right? Okay, the lossy structure is related to the so-called loss tangent, right? Ideal case, the loss tangent, okay, should be 0, right? Okay. However, in reality, practically, as low as possible is better. Of course, cost will be higher. Okay. Typical PCB, the loss tangent is 0.02. Okay, very cheap one. FR4. Typically, for very high-end one, then loss tangent should be as low as possible, 0.0001. Okay, 10 to minus 4, right? Okay, or low 10 to minus 3. Okay, anyway, characterized by this epsilon and loss tangent. Okay. This is so-called very popular microchip line. Okay. So this, as for this transmission line, this subject is characterized by epsilon r and loss tangent. Then subject thickness, right? As for this transmission line, then line width. Okay. So all these parameters will determine the. For us, bear in mind, we need to look at what parameter. Yes, good. So why we need to look at this parameter? Because later we need to look at the impedance matching. Okay. For instance, this transmission line could also I have last time also I showed you antenna, right? With a transmission line. Okay? With here. Actually this section, this short section is transmission line connected with this is a connector. We need a medium, right? Okay? Another end is the antenna. Okay? Why we need to look at the impedance matching? Okay, for instance, this connected with a transmitter, power amplifier. Okay, right? Minimum if all this impedance are matched to 50 ohm. Typically we use 50 ohm. Okay, then minimum reflection, right? Then most of the power can be transmitted to outside. Okay, right? This is one kind of subject. It's called FR4, very popular, low cost, very welcome by industry. Right? This is bottom, right? This is bottom. Then this is the so-called substrate. On the top is the trace, right? On the top of the trace. Okay. You can design this quickly. Okay. Right. So, in addition to the very popular microchip line, later on we will calculate the characteristic impedance. Right? Also based on the characteristic impedance, you can determine the line width. Okay? So we will give you a very compact code. Okay? To do this work. In the meantime, we will still need to give you a set of formula. Okay? To help you to understand those behind of the code. Okay? Behind of the code. Another type of transmission line is so-called coplanar strip line. Coplanar strip line. What is coplanar strip line? Is on the top, the signal and the ground transmission line at the same layer. We call this coplanar strip line. Okay? Coplanar strip line. The third one is coplanar waveguide. This waveguide is not this waveguide. Okay? Bear in mind. Okay? Coplanar waveguide is this waveguide. Okay? This waveguide. Coplanar waveguide also very, very popular. Okay? Although for us we may not use it often, right? Okay? Coplanar waveguide, in short, is CPW. Okay, CPW. So, in some textbook or in publication, technical publications, you could see the short form CPW. Okay, means coplanar waveguide. Sometimes notice this, the black one is ground plane. Okay, this is the signal trace. Okay, sometimes we don't have the the ground at the bottom. Okay, we only have this. Okay. So there are two types of CPW. One is like this, is ground back CPW. This is normal CPW, right? Okay. So also we have the fourth one, strip line. Strip line. Okay, for this strip line transmission line, you can compare this and this. Okay, what's the difference of this transmission line and this transmission line? What's the difference?
Shielding.
Yes, shielding. Right. This strip line has better shielding. This transmission line, some EM wave will be transmitted outside the subject. Right. Most of EM will be confined to the subject. Okay. So, however, this fabrication complicated compared with this one, right? Okay. Also, some other, for instance, these collection cables can be considered as one kind of strip line, right? Can be considered as okay. This the extension of the strip line. Anyway, the microchip line we will emphasize on the microchip line. Okay. The basic structure we have already mentioned. One substrate with conducting metal and booth either side, right? Then here we highlight this transmission line. Emphasize this transmission line. Okay. This transmission line, the main advantage is simple, not expensive to fabricate by using the normal PCB technology. another advantage is easier to integrate it with other passive and active circuit. Passive and active. Passive means those devices don't need bias, right? Okay. Active, for instance, those amplifier, right? Okay. Passive like inductor, capacitor, filter, right? Okay, passive device. So means the microchip line are very popular for integrated circuit. So can give us small size. Also the weight can be very light. This is one example of hybrid microwave integrated circuit. Hybrid HMIC, hybrid integrated circuit. These are very popular. It's one kind of circuit for maybe for defense application, right? For defense application. Also can be used for other communications. Okay. Even for chips, okay, for IC, transmission line. Inside definitely need a different kind of transmission line. Maybe microchip, even for high-end could be CVW. Okay. The package since some students, many students are working in the semiconductor industry, right? Okay. So if you look inside of the chip, although it could be different sectors, if you look at inside, for those chips, when those chips link with other parts, those chips need the transmission line, okay, to link with other parts. Right? So definitely transmission line very important, essential, fundamental to the subsystem, right? For those parts, very important. Impedance matching. Okay? So characterize the transmission line. The characteristic impedance is very important task. Very important task. So sometimes as RF engineer, your job may not that difficult, right? Those chips, later I will show you actually in our foreign session, the amplifier part. Okay? No chips you can order, right? Okay? Then what you need to do is just design those transmission line. Then assemble those chips together. Okay? Especially for those common frequency band. For instance, Wi-Fi, right? Bluetooth, those. However, for those frequency not very common, then you need to design from scratch from a transistor. So in our module, also we will introduce help students to build this field, okay, by using the industry level software. How to design amplifier by using a transistor. Also, we will give you some example to build amplifier just by using commercial available chipset. Then the task is very straightforward. So in reality, as RF engineer, most of the time you could just use the commercial available chipset. So your work becomes very straightforward, right? Okay. So, however, you need to understand those specifications. You need to understand the language of those, right? So you can benefit from this module. Okay. So then you can also interact with with those systems in the air. Okay, also we mentioned the difference of the tube line and the microtube line, right? So as the gentleman mentioned, most the ground plane can be used as a shell. So the electric magnetic wave EM can be confined inside, right? So then for this transmission line, here notice the velocity. So this is quite straightforward. Velocity is this speed of light in free space divided by this. Okay. However, for this transmission line, notice not all EM, this EM are confined in the subject. Right? Some EM will leak out. Okay. So turns out only the transmission line width is very wide. We can consider this wide line. Okay. The velocity is like this. Can be equal like this. Okay. If it is narrow, typically not very wide, right? It will be linked with characteristic impedance. Okay. For that case, how can we handle? So then we will introduce so-called effective or equivalent permittivity, relative permittivity. Okay, is equivalent or effective. This guy is for finite width. Typically, we are handling the finite width transmission line, right? Okay. So from this equation, okay. For instance, okay, I will not write this equation. However, we will look at for the limit for instance, this W is very wide. Okay. Then this close to 0, right? Close to 0. Okay, close to 0. Close to 0, then this is 1, then this will be equal to epsilon r. So largest value, upper limit, epsilon e is epsilon r. Okay, for finite case, then epsilon e is less than epsilon r. Okay, less than r. Okay, so what is the physics behind this? For finite case, the EM, some EM will be leaked out. So here we mainly care about those EM inside the substrate. Okay. So now we assume in the whole of this case we have another subject, okay, equivalent to this phenomenon. Now the dielectric constant is from E. Okay, so for this case, all the EM lines are inside this subject. Okay, this we call E. This we call E. Okay, now let this actually this phase velocity or propagation constant. This propagation constant is more important. Although here we introduce a phase velocity here, Vp is phase. Here D is dielectrical. in this dielectric. Here A means air, in the air, okay, in the air. So in dielectric material, the phase velocity is c divided by epsilon e. Now it's epsilon e, okay. This parameter is more important. This parameter. So in our EE4101E also we mentioned this times times the physical length is the electric length, this parameter. So why this parameter is 6. You cannot understand easily if you only look at this data, right? But if it times with the physical length, for instance, this physical length of the transmission line, then you can understand. It will represent here the phase delay. Okay, will represent phase delay. Okay, so this is inside this substrate, the propagation constant in the times the epsilon r of relative equivalent relative permittivity. Okay, this is free space propagation constant, right? What is free space? Means outside free space. On the top, right? On the top. Inside of the subject, we need to use this. So be careful, okay? So this is common mistake, okay? Common mistake. Be careful, okay? Okay, try to make use. Since in our previous module also we mentioned, okay? For those students who spend time travel to our class, will have more advantage compared with other students who cannot be available to our class due to various different reasons, right? Okay, try to improve, make full use of our class to help yourself, also help us, right? Help us is help us is this, since you spend your effort, make your effort. Finally, we help us. We can give you a big grade, right? Okay. Here is common mistake in the subject. You should use this, right? Okay. Don't use this in the subject, right? Above in the free space, you use this. Okay. In the subject, you should use this times the square root of this complete. So